Hi guys, let's continue our adventure and see how functions resolution is performed behind the scene. We have this code, but we don't know yet the algorithm used to generate the function hashes. We have to first study the assembly code. We'll start from this point where the function resolution begins. This address gets popped into EBP as I've commented here, and then executed. One of the difficult parts is actually the obfuscation created by the series of jumps and the junk code. In spite of this, we can still see important markers in the code. One is the module name, which gets placed into this ESI register. Afterwards, a hash of this name is computed in this portion of the code. Notice this loop over here. Over here, and notice that each letter from the module name is loaded separately. A comparison here. A value that is lowercase a, so this comparison converts the name of the module to uppercase letter by letter. Then some operation is applied on each letter. This is the conversion to uppercase over here. And the operation performed to create a hash is this one over here. Let's see. A rotation followed by an addition. Straightforward. After we have a hash of the module name, the code computes a hash for each function in the module. The algorithm is almost the same. After we have each module's address, we can extract all the exported functions, get all the function names, and for each one, generate a hash using this logic. Ignore this junk code over here. This portion here gets the function names from the exports section. Over here, then placed into ESI register. Then hash resolution starts with this code over here when the EDI register is zeroed. This portion zeroes the EAX register, then loads the first letter of the function name. Applies some operations over here. Pretty simple, almost the same as for the module name. A rotation, right, followed by an addition to EDI. So keep in mind the hash is computed in EDI register. At the end of this loop, we will have the function hash in EDI. As we know from dynamic analysis, if this hash matches, this shellcode will jump at the end of execution to that address, which will be in EAX. Let's see where is the jump. A lot of flow obfuscations, which can become pretty confusing. This is the jump. Let's also add a comment. Jump to the result function. This is a very important point in our investigation. Now let's save the analysis. There are a few important things to remember about this code. The first is that the hash of the function to be resolved also includes the hash of the module. So the algorithm first computes the hash of the module and then adds that to the hash of the function to obtain a value that gets compared with the parameter initially passed to this routine. Let's go back to function 1 where we have the first example. In function 1 we had virtual alloc represented by this hash. It might sound slightly confusing now, but let's try to recap the logic here and make sure things are clear. So there is an algorithm that computes the hash of a function. It takes into account also the module name. That hash is compared with different precomputed values. If we have a match, a function is called. For example, in this case over here, this one was virtual alloc. The code that does all these can be confusing to analyze, mostly because of the obfuscations. Anyway, to represent that code in Python, this is the rotation part, the rotation right. And this function computes the hash of the module, pretty simple, rotation plus addition. Similarly, the hash for function names uses the same logic, rotation plus addition. Exactly the same. And in the end, this hash gets added to the hash of the module. Something very important to have in mind. Module names are actually Unicode. So the representation of Unicode contains characters followed by zeros. I've taken this into account in this logic over here. For each letter in the module name, I've appended a 0 to the list. Another trick to note about this shellcode is that function names used in the algorithm also have a new line terminator at the end. Lastly, another important point. When we add the hash of the function with the hash of the module, we need to make sure to limit the result to 32 bits. That's why we do a binary AND operation with the maximum value on 32 bits. This line makes sure that the result can be represented on 32 bits. Go back to the code and recheck all this logic. As an exercise, try this for yourself and make sure that you can use both dynamic and static analysis approaches to figure out what functions are being called. This simple code here is translated from this sequence over here. Same for hash of the modules and hash of the functions. Alright, if this sounds difficult to digest, spend a few more minutes on it. If you understand it properly, this is a very useful technique to know, because not only Metasploit, but a lot of other frameworks and payloads out there use this technique to hide the functions that are executed. Okay, thank you very much for learning with me, and make sure to practice on your own. Do study this technique until you understand the assembly code involved in these functions. Take care. Cheers!